Hi all. So till now we have studied about Biot number and lumped body. In this class we will going to start the discussion further, and just for the recap, Biot number we have seen it is the ratio of conductive internal resistance to the convective internal resistance, and it is calculated on the ratio of volume by surface area of the body. All right, and we also saw that volume by surface area of the body is nothing but the characteristic length. So if we are calculating for, let's say, sphere, so it will be 4 by 3 pi r cube by 4 pi r square. All right, so it will come out to be r by 3, or in diameter sense we can write like d by 6. So this is the characteristic length for the sphere. So like this we can calculate for any type of body. Okay, and we also saw that Biot number is the ratio of conductive resistance of the solid and the convective resistance offered by the fluid which is flowing outside the solid body. Okay, so it is the ratio of these two. And we also saw that Biot number represent the temperature drop within the body to the temperature drop between the solid surface and the surrounding fluid. So if this temperature drop and the surround temperature drop within the solid, and the temperature drop between solid and the surrounding fluid is zero, then the body we will call as lumped body. And we also saw that lumped body is just imaginary concept, and for lumped body temperature changes only with respect to time, which is not with respect to the location inside the body. Okay, so but Biot number cannot be zero in reality, but it can approach to zero. So for simplicity, in the textbooks you can find that if this criteria is met for the Biot number, then the real body can behave like a lumped body. So by intuition you can say that Biot number will be small when thermal conductivity of the body is large. It means body have very high value of thermal conductivity. It means the body has a high tendency to conduct heat. Moreover, if the body is placed inside some quiescent ambient condition which offers very low heat transfer coefficient, in that case also Biot number will be small. And for the case where characteristic length, it means volume by surface area of the body is small, so if these parameters combined together forms the Biot number less than 0.1, then we can say that lumped capacitance method is valid, or body can be assumed to be lumped. Okay, so now we will start our discussion on lumped heat capacity method. So before starting that method, we have to introduce you to this terms. T naught is the initial temperature of the body. It means that T is equal to 0. It can be some low temperature if the body is going to heat, and it can be some high temperature than the surrounding if the body is going to cool. Okay, and T is the temperature at any time T. All right, T infinity is the surrounding fluid temperature, and M rho C V AS is the mass, density, specific heat, volume, surface area of the body, so forth and so on. And if T naught, initial temperature of the body, is higher than the surrounding fluid temperature, then the body is going to cool. All right, and when the body is going to cool, it will release heat. So it means no heat will come out, no heat will come inside the body. So rate of heat entering inside the body will be 0. and vice versa for heating case. Alright, so starting the analysis for lumped heat capacitance method, these are the assumptions that there must not be any heat generation inside the body. All thermophysical properties like rho, Cp, thermoconductivity, etc. are constants, and radiation heat transfer is neglected. We will see that how it will impact if we relax this assumption number 3. All right, for the time being we are not relaxing this assumption. It means we are imposing this assumption that radiation heat transfer is neglected, and heat transfer coefficient and surrounding fluid temperature is also constant. Alright, so consider that suppose there is some general shaped body which is at T0 temperature. So, and assume that it is a lumped body, right? Alright, and it is placed in some hot fluid. You should ask that I am specifying only a single temperature to this body. When we can specify the single temperature to a body? When it is a lumped body. It means at every point inside the body temperature is T0. At every point. Alright, so if this lumped body is placed inside the hot fluid initially, let's say T is equal to 0, and surroundings are T infinite and H, and suppose we take out this body out of this hot fluid and it is allowed to cool. So we are doing the analysis for cooling of lumped body. All right, so this body at particular time T will not be at T0 temperature because it will start releasing heat to the ambient, right? And at every point temperature will be T. As it is a lumped body, so there will not be temperature gradient inside the body. So only with respect to time temperature is changing from T0 to T, and further if we go in time temperature will further drop. All right, so if we consider a control volume around it, and heat is going out of this body by convection and radiation also in general, but we are assuming that there is no radiation in the assumption, right? So only convection is the heat transfer which is going out of this body. So applying the energy balance, Q in minus Q out plus Q generation inside the body is equal to rate of heat stored inside the body. All right, so since it is a cooling of the body, no heat will be coming inside the body, all heat will be going out. And one more from the assumption number first, this term will also be go out, and so we will remain with rate of heat transfer out and rate of heat stored inside the body. And what is rate of heat stored? That is nothing but the mc del T by del T. So till now we have studied the steady state heat transfer, and this term was going to 0 in those cases, but this is unsteady heat transfer, that's why this term is not 0. All right, and if now we want to write this Q dot out, for writing it we must know the heat transfer coefficient on the fluid side and the T infinity temperature and the surface temperature. So on writing like this, H times surface area times T minus T infinity. T is the surface temperature and it is the inside temperature of the body also, because it is a lumped body, so everywhere temperature will be T. All right, and writing m as the rho times volume of the body times c times delta t by rho t, and t is a function of time only. Since t is a function of time only, we can write the partial derivative as ordinary derivative, rho vc dt by dt minus has t minus t infinity. So this is a ordinary differential equation, linear differential equation, and you can use variable and separable method from your 12th standard mathematics, calculus, and we can integrate it like this: t minus t infinity dt by this, and if we write this as let's say m, this is, let's write as m only, mc times has dt. Alright, and if we integrate it from, let's say t is equal to 0, at t is equal to 0 temperature is t naught, and at time t some temperature t, so we will have ln t minus t infinity divided by t naught minus t infinity equal to minus HAST divided by MCT. Sorry, I made a mistake here. This should be HAST by MC. Alright, so we can convert this ln to exponential. T minus t infinity divided by t naught minus t infinity equals to exponential of minus HAS divided by MC t. Alright, so this is the equation. Then this equation is valid. We can write like this, and this equation is valid for heating as well as cooling. Okay, for heating we can draw the graph of this equation. Let's say on the x-axis time we have, on the y-axis we have temperature, and let's say we are starting from some high temperature for cooling of the body, and this is the ambient temperature, very low temperature. Okay, so at t is equal to 0, temperature will be t naught, it will drop, and if we allow the body to cool for large time interval, it will reach the T infinity temperature. You can cross check this by putting the value of T as infinity in the above equation. You will get T as a function of time as T infinity, and T is infinite there. Means if we put large value, then we will have the temperature of the body near to atmospheric conditions. Alright, this is for the case of cooling. If we want to draw the curve for heating, the curve will take the shape like this. Here again, temperature on the y-axis and time on x-axis, and let's say body is heating, and let's say surrounding temperature is high. Alright, and initially the body is cooled, body at cool temperature, and it is going to heat like this. So this is the case of heating. Alright, so next time we will do the analysis further for this lumped body. Thank you.